So here we are at this last week that's on the calendar here, and so I'm going to have to post the new calendar. I'll do that tomorrow for March. But right now I want to show you that you have these pre-lectures due, and they're all up now, so you can do them. They're really simple. They're on regression. And so what we're doing today is we're finishing up ANOVA, chapters 21 and chapters 22. And unfortunately, we don't have any pre-lectures on ANOVA. We just haven't made them yet. So that's why it's skipping here. Oh, it says chapters 22 pre-lecture. There is no chapter 22 pre-lecture. It's going to be 23, 24, and 25. So that's a mistake. It should be chapters 23, 24, and 25. And then this bonus survey, we haven't posted that yet. I'll do that tomorrow. So you have the 3 pre-lectures posted, and you have the homework 12 that's going to cover chapter 22 that we do today, the end of 21 and 22. It's not going to, 23 starts with regression. It's a whole new part. It starts with correlation and regression. And so we're going to start that today, but the homework for that won't be due till next Monday. Okay? So now you're probably wondering, so here's, as you probably know, I posted the exam keys. And if you just walked into class, you can pick your exam up right here. And if you're watching at home, you can come to office hours to pick up your exam. And there's 2 keys here. You either have in the heading here on your exam, you either had capital letters here, in which case you had this key. They're very, very similar. Basically similar, same problems in different order or slightly differently, different numbers. But they're very, very similar. And in the other one, you had in the heading a small stat there. So those of you who are watching most, unfortunately, I'm trying to still get a way to get your error sheets from Compass in a form that I can send you your individual error sheets. Scantron people don't know how to do it. They sent me a file. They said it might work. So far, it hasn't. So what does that mean for you? It means that you can come to office hours and I can show you your error sheets so you can see what you got right and what you got wrong, because your exams aren't graded. And you can also pick up your exam. But I'm going to still work on it, and hopefully maybe I'll find a way to send you your error sheets so you won't have to traipse into the office. So that's, and people did really well. I was pleased. The average was about 84, 83 or 84, and the median was 86. And that's perfect. Not too easy, not too hard. It's just really, that's where I wanted it to be, so I'm really happy about it. And there's one more exam, and then there's the final. And they're all midterms, all worth 25% of your grade, and the homework's 25%. So any questions on the exam? Okay, so now why don't we go over to the document camera right now, and we had just a little bit left to do. So this is page 109 here that I'm looking at. We did this example, we started it, but we'll look at it again here. So remember what we're doing here. We're looking at comparing group means to see if any of them are different. So we're looking at multiple means at the same time. So here's some survey data from back in the spring of 2014. So a sample of 858 Stat 100 students rated how strongly they favored gay marriage on a scale from 0 to 10. 0 means they're very much in favor, 10 means they strongly opposed. And then they also identified themselves by their ethnic group. So assume these were randomly sampled from a much larger population of Stat 100 students, okay? So we see differences, like here's the histograms for each of them. So we see differences in the means in our samples. For example, the largest mean we got was right here, and that was for those who identified themselves as black, and the smallest we got was here, and that was for those who identified themselves as, is that the smallest? No, this is the smallest, right? This is the smallest, and those for Hispanic, so this is not the smallest. So this was the biggest, the largest, which meant the most opposed to gay marriage, and this was the smallest, right? And they're different, and we want to know whether these differences, even though, you know, everyone seems to be for gay marriage. If the midpoint is 5, when you sort of didn't care one way or the other, so everybody seems to be for gay marriage, but Hispanics are more in favor, and this group is the least. All right, so now, so it looks like there's substantial differences, but maybe they're just due to chance variation. It's hard to tell. So we're going to do a ANOVA test to see. We're going to look at the between group and the within group variation. Okay, so here's the null, that in the population of U of I students, that all these means are equal. It's just we happen to have some sampling variation. Do you understand? And the null is, the alternative is no. Not that they're all different, but that at least one of them is different than the others. Not all of them are the same in the population. So then I gave you, right here, these two sums of squares. So what was this? This is the total variation. Remember, this was, if you sum all of them from y equals 1 to what, 858, and you subtract off their overall mean for all of them and square them and sum them up, that's what you get. And what do you do here? Here, what you do is you say, okay, we're still summing up all 858 people, but we really only have 5 squared sums. For everybody in this group, for example, we're going to get, so for all the y's who are white, we'll get we're going to subtract off, we're going to take this mean, we're going to say that's what we estimate them to be, the group mean, and then subtract off the overall mean. So we really only have 5 different squares here, right? Because we have this mean subtracted from the average, this one subtracted from the average, it's squared, etc. But for each one of those, we're going to multiply it by how many people we have, right? Okay, so that's what that is. And then what's the within group? Then we're going to take like in this group, we'll take all 448 people and subtract their mean off. How does that differ from this one? Here it's the overall mean. Here we're just seeing the within group spread, how spread out they are from their mean. Okay, so it looks like that. But this was done for you, so you don't have to, this is the within group, so it's everybody minus their mean. Okay? And so these two are already done, so you don't have to do this one. I mean, you could, but you don't have to. What do you do here? So how do you get this? You just, remember they have to sum, so you just say 8953 minus 330. And that's how we got 8623. So this plus this sums to that. So any questions so far? All right, now the next one, the next column here is the degrees of freedom. So the degrees of freedom, remember, are n minus 1 for the total, everything except the mean that's already been estimated, so already been calculated. So it's n minus 1. So in this case, what is n minus 1? It's 858 minus 1, so we get 857. That's what we get there. And if you can't see because this pen isn't too dark, just come up closer, okay? Are you doing okay back there in terms of seeing? Okay, so now what about the degrees of freedom for this one? Well, remember, this one is the number of groups minus 1. So the number of groups minus 1 is what? We have 5 groups minus 1, so that's 4 degrees of freedom there. And the last one is n minus g. Now remember, once you figured out these two, they have to sum to 857, so we already know that this is 853, but if you wanted to do it directly, it would be n, our total sample size, which is 8953. Excuse me, our total sample size is what? Our total sample size here is 858. 858. It's this right there. Let's put that up there. So that's n right there. And we're assuming we're taking it from a large population. Don't ever use this, like I almost did that again, right? That's ours, okay? So it's 858, and then we're saying minus 5, right? So we get 853. So those are degrees of freedom, and they sum. So now, what are we going to do next? We just divide to get our mean. Our mean, it's the average of the sum of the squares for both of these. So you divide by its degrees of freedom. So you have, for the between groups, you have 330, and you divide by not g, but just you tweak it a little bit, and 1 minus, right? And we got 82.5 there. And same for here. So this is, we take what? We take our total right here, and we don't divide, we're almost dividing it by n, but we divide it by n minus g, and it's 853. And so we get 10.1 there. So those are our mean squares. Okay? And now we get this F ratio. And F is equal to the ratio of those two mean squares. It's the mean square between over the mean square within. So we get 82.5 divided by 10.1. And that's 8.16. And that is our test statistic that we're going to use. Now, right? Because this is a measure of how different, the top part is a measure of how different the groups are, how far they are from what we'd expect, from the overall, how different they are. And this is a measure of sort of the overall scatter within the groups. Okay? The standard deviation, or the variance within each group. And this is like the variance between the groups. Okay? So now, what do we do with that? How do we evaluate it? Well, we have these two sets of degrees of freedom, and here they are, 4 and 853. So we have to look at this table. Now the F table has it's many pages long because you have two sets of degrees of freedom. And so I looked at this one. This is for the critical value at what? So this isn't our usual 5%. This is at another way you'd call it is alpha. This is 1%. You could say P or alpha equals 0.01, same as 1%, not the usual 5%. Okay, so where do we look on here? Well, here's the degrees of freedom for the between group in our numerator up here, and that's 4. So you're going to look down here at this 4, because that's our degrees of freedom for the numerator. And then we have 853. So it's in between 500 and 1,000. So that's 853 are the degrees of freedom. This is called degrees of freedom 2, and this is degrees of freedom 1, we could call it, for the numerator, and that is 4, and this is 853. So it's in between 2. So the conservative thing that most people do, if the degrees of freedom is between two lines, most people use the smaller. They're so close here, and ours is so much bigger than either of them, but that's sort of the rule of thumb. Use smaller degrees of freedom. So we're going to use the smaller one because, think about it, the bigger your sample size, the more evidence you have. So we're being conservative and saying we don't have quite as big a sample size rather than to overestimate our sample size. So that is the critical value right there. That's the one we're going to be using. So what does that mean? So to draw it out, we could draw out an F. And that critical value, remember F can never be negative, so start it at 0. Remember the mean of the F we'd expect to be about 1. Now here, our critical value right here, this is our critical value, this is our F star right there, and that is equal to what? 3.357, okay? And then it says only 1% of the area of the curve is beyond that. Now where's our F? So here's 4, 5, 6, well, 7. I'll just pretend ours is there, even though it's even further. I'll just pretend RF is right there at 8.16. So it's way on the tail of the curve. I'll try to draw the curve for you. It's going to look like only 1% of the area is there. So it's going to be really sort of like something like that. And so what are we talking about here? At our critical value, this is the alpha right here. This means that from here on in this direction, P, this is equal to 1%. That means our tail, this tail here, because of that, this is 1%, okay? That's what that means. Now, where are we? We're here. So what's RP? I can't even write it here, but you know RP is a lot less than 1%, correct? Let me see if I can make it better looking. I'll need more paper here. Here you go. Okay, so if we went, this really extends out, right? So RP is the area from here on out. So RP is much, much less than 1%. Because this is where, this is our F right there. Okay? Does that make sense? So we have a tiny, tiny p-value. So what does that mean? It means the likelihood that we would see this big an F ratio, if the means were really the same in the population, is tiny. So we're going to reject that null. Because when the null is true, these between group differences aren't very big, because the null is that the groups are all the same. Does this make sense? So that's what we're doing here. So what we'll say, since RF, we'll say RF is way bigger than F star, than the critical value, right? So what that means is what? So it means that our p-value is way less than alpha. P-value is less than what? Is less than alpha. In this case, usually it's 5%, but in this case, it was set at what? Alpha equal to 1% here, because we're looking at the critical value at alpha 1%. So that's what we're saying. So what do we conclude? So we reject the null and conclude what? Well, let's look up here. What was the null? So here's our null. If we're rejecting it, we're concluding they're not all the same. That doesn't mean everyone's different from each one. That means we conclude what? When we reject the null, we're concluding that they're not all the same. So at least one of them is different. So we reject the null and conclude at least one of the means is different in the population. Okay, so that's the idea. Now, so this is the overall test. You do this as a first step. You do this overall test here. This is the overall test, looking at them all. And then, now that we've found significance, we can move on and see which one of these is different. So then what we do right now is we go back and we do t-tests between them to see which one is different. Okay, so that's what the next chapter is about. But before we do that, we should look at these assumptions on the next page for ANOVA. So let's look at those just for a minute. And it says, in order to do this F test, we have to satisfy a bunch of assumptions that are going to sound very similar to the t-test. Okay? So, first of all, our random samples are independent. This is true of all our tests. This means that every draw is independent of every other draw. Whether or not you draw higher on one, like we get somebody who has a high opinion on one, that doesn't mean we're going to get a low one on the next, right? Tells us nothing what the next draw will be. It's not like there's groups of identical twins or something that would have the same opinion, or clones or clumps of people. They're all independent. And you'll see this expressed as the errors have to be independent. You're going to see often that the errors are distributed, are something called IID, which means independent, identically distributed in higher classes. But let's just, you're going to see it here. It's just a language you'll see a lot. So they're independent. Now, the variance of the populations must be equal. What does that mean? It means that those sum of squares within the standard, not the sum of squares, the variances within the population are the same. That's the assumption. That the variance of the population must be equal. Even if we see them different in our sample, we're assuming they're the same in the population. If they weren't equal, then we'd be giving more weight to the group with the biggest variance. Why? Because the sample mean from the population with the bigger variance is likely to vary more from sample to sample. So in any particular random sample, it's likely to differ more from the other group means, even when all the population means are the same, right? It's going to vary more, so we're going to give that too much weight, and we don't want to do that. So this only holds if all the populations must be equal. So this is identically the same variance, okay? And then the errors around the group means are approximately normal. The F test, like the T test, only works if the populations are close to normal. So let's look. So what that means is that we have to assume that even though these samples look really different here, that in the population, they had the same standard deviations. Let's see what their standard deviations are. Do we have a... Here. On the next page, we're given these standard deviations. They look like they're somewhat spread out, right? They're not exactly the same. And that looks pretty good. What doesn't look good is doesn't look normal, right? I mean, we're not talking about the distribution of the sampling mean. We're talking about the data itself the populations itself have to look normal. And these really don't look normal. So what do we do in cases like that? I really should be not using the F if I wanted to be a stickler about it. But let's go ahead and do it anyway, and people do because they say the sample sizes are pretty big. But I just want to tell you that we're going to really, in this class, what we're going to do when something like that's violated, even with this example, we're going to go back to it, and let's write down what we're going to do. So this looks violated here. So I would be concerned. So what I would do, and what we're going to do later, we just haven't learned, is another technique. So we're going to examine these assumptions later. So we're going to look at plots of errors and residual plots and all that. And if we think some of them are violated, we're going to, like I think this one looks violated, we're going to we can use other methods to get at these p-values. So when assumptions are violated, so when the assumptions are violated, we'll use other methods to get at those p-values. And one that we're going to use that I think you're really going to like is pretty much enacting a randomized experiment. So there is going to be a simulation. And I think you're really going to like it. And that's it's called re-randomization methods. And they're very popular and they're very cool. And this is in chapter 39. But we first have to understand what regression is and correlation coefficient before we can do that. So that's what we're going to be doing. So that's to come. So it's not what I really want to emphasize. There's not just one tool that we have. We have in statistics, we have a lot of tools. So we'll see how our p-value using this test with some violated assumptions, slightly violated, how it compares to other methods and make sure they agree. And this is what you should always be doing. We just haven't learned enough yet, but we'll get there. All right. So now let's look at our summary here. So this is a summary for the overall ANOVA test, okay? So we're comparing, and for comparing group means, but I want to put it in the context of all our hypothesis tests so far. What do they have in common? So this is useful to read. So it says, all of our tests are a statistical check to determine whether some effect you observe can be due to chance variation. And the ANOVA was whether these differences in group means can be due to chance variation or not. And what the numerator of the test statistic, like in this case the between group means, is a measure how large that effect is. The bigger differences you see between the groups, that's a strong effect. For example, I looked, as soon as I got your exam scores back, there's 7 sections in this class. There's you guys lecture at 9:30 here in 150 Animal Science, L1. There's also the online, and there's also 5 small sections that are all doing the same thing, all taking the same exact test. So the first thing I did was I looked at the group means between them and did an F test, exactly. And I have it on our data program, and you can look, we'll look at it later, and maybe post it as a review problem. So you can see that. And I didn't want to reject the null. That would have been terrible. That would have meant that one of the groups, there's something going on with one of the sections that's different. Luckily, it was far from being rejected. It was great. They're almost the same, but I just wanted to make sure. And so that was great. So sometimes you don't want to reject the null. You want those group means to be equal. All right? And the denominator is a measure of how large the chance error is. So we've looked at these 2 basic situations. One where we basically just had the Z and T test, where we're looking at the effect can just be boiled down to a single number that's positive or negative, just a single number. And then we had these chi-squared and F tests where you cannot express, they can't be expressed as a single difference, including a sign, because we're looking at a whole pattern of differences, and we want to know if the whole pattern differs from what we'd expect under the null. So in this case, we have to square, this is what makes it more complicated, a set of differences and combine them. So the positive and negatives don't cancel each other out. They can never be negative. Okay, so now, but for all of these significance tests, the bigger the test statistic in absolute value, the bigger it is, you see a big one test statistic, the smaller the p-value. You're further out on the tail of some distribution that assumes the null's true. And the likelihood of getting that big a test statistic is what the p-value gives you. So if you're really far out and have a little area on the tail or 2 tails, that's the likelihood that you would see such a big test statistic or bigger if really nothing was going on, if the null was true. So that's when we reject the null. Now, there are 2 factors that influence the test statistic. One is the size of the observed effect, and the other is the sample size. Clearly, if you get a bigger difference, you're more likely to get significance. And also, if your sample size is bigger, the bigger sample size, the more likely you'll be to get a significant result, because you have more evidence. You're going to have smaller standard errors. Okay, so, and this is what we're doing for ANOVA here. This was our ANOVA summary. And we went through this before. Do I have to, this is basically it. You do need to know what these mean, so might as well write them again. So this was the sum of all the individual quantitative results. You know, everybody, okay, you have two variables. One is your group, and the other is some quantitative, right? For all ANOVA, you have two variables. One is your group, which group you're in, and the other is your quantitative measurement. So that's why I'm calling them Y's. You're usually predicting the quantitative measurement. So here are the Y's. This is the total sum variability of the Y's. If we multiplied that by what? So SST, if we multiply that by n, not that by n, if we take the standard deviation, let's do that. If we take the standard deviation and square it and then multiply by n, that's what we got here, right? Because if we took that and divided it by n and then took the square root, we'd get the standard deviation. So that's what this is. It's just that first step we do, then we divide by n, and then we take the square root, and that gives us the standard deviation. So that's what SST is. Okay? And SSW, what's that? That's all individual points from their group mean squared. Okay? So then, and what's this one? This one is the group mean minus the overall mean squared. So that's the idea here. And one thing more I should say is what? So when we get to this part here, the mean square error, right? Look what we're doing. That's the sum of the squares within each group, right? Then we basically divide by a tweaked n. So that gives us the variance within the groups. And then if we take the square root of the mean square, you're probably wondering why I'm switching between model and error. And this model is between, we can cross it out. It's because it's an example of a much, and this is within. This is because we're going to move on to regression. And this is sort of how this is a particular example of regression where we have a categorical X predicting a quantitative Y. So in generally you see model, our model is predicting some variable from the group you're in. But here we haven't gotten that far. So right between, within, and so then right here, this is within, M mean square within. And so that is equal to the standard deviation plus, because we divided it, we tweaked it. Otherwise, it'd just be the standard deviation of what? Of the within groups. Some people call it error because it's error around our group mean. Okay, so that's what we've got here. And now we're ready to look at how to do multiple comparisons. So this is called t-tests for multiple comparisons. So we're just basically going to do a two-sample t-test. It's going to be just like the two-sample t-test, but there's just going to be two differences. First, let's look at this. So once the f-test tells us that at least one of the group means is different from the others, like it just did, how can we determine which ones? Well, we can do t-tests between pairs of group means to see which is significant. Now remember, we had the observed difference in means minus the expected, which was 0 under the null, right? Observed minus expected, that's equal to 0. That's why I didn't even put it down here. Okay, the observed minus the expected over the standard error for the difference. So we have the difference between the group means, and now we have that Pythagorean theorem here, right? The sum of the, so you take the standard errors from each one, square them, and then take the square root. So looking here, what we would have done is we take, if we wanted to test like our biggest two difference here, which was these two right here, what would we have done? We would have taken the difference between these two, and then here's the standard deviations. They're both different. So we would have multiplied them, made them a little bit bigger, right? Get the plus by the square root of 85 over 84, right? And the square root of 100 over 99. We could have done that. And then we divide. So this is what we have, right? So we take two different ones, and then their averages. So the standard error for the average is SD plus over the square root of n. So we'd have two different ones. So in here would be, for the blacks would be 84, and this would be 99. And that's what it would look like. Okay? And we've done that. But we're going to change it a little bit because of this. One of the assumptions of the F-test is equal variances in the population groups. We just saw that. So this means we need to estimate the same SDs for all the groups, even though our sample SDs will vary somewhat. If they vary too much, then we can't do ANOVA, and we have to do something else. Okay? So now these look pretty good. They're pretty similar. That's not the violation. The violation looks more like the normality violation. This looks pretty good. But so now what do we do? So what is our pooled estimate? Well, it's the square root of the mean square. Why did I say the mean square between? It's the mean square within. Sorry, it's right here. It's the mean squared within. So let's change this so you don't get confused. So what is this? This is between. And what is this? This is within groups. Okay? Between and within. So this right here, we got the mean squared between. This is the mean squared within. This is the mean squared between. This is the mean squared within. And this is the square root of that. So this is the square root of the mean square within. And that's what that is. It's the square root. This is equal to the square root of 10.11. And just make sure I didn't say it wrong. Yeah, I said it right here. Okay? And that makes sense because this is the within. We're looking here. It's within each group. We're making an estimate within each group of some sigma. All right? Maybe if I draw let's just, since we're right here, let's look at what we're doing here. What we're going to be doing is you're imagining that in the population you have blacks, if we're going to do these two groups, right? Students, and you have Hispanic students. And you get this difference in their samples, and the null is what? That, yeah, you get this difference right here in opinions on gay marriage, but that's just chance variation. If you did it again and sampled 84 from here and 99 from here, and there's thousands of tickets in each, this is the whole population, right? So this is assume samples are random from whole population, all U of I students. Okay, so you have thousands of U of I students. We sampled these numbers here without replacement. That's what we did. We drew from here, and then we got these statistics. But our null is about the population. So it's about what? That the average for blacks and the average for Hispanics are the same. So that is our null. And the alternative is two ways. We just think that it's different. We're not specifying a direction. So the alternative is that they're not the same. And the reason we see such a big difference is because it reflects a real difference here. We don't know what it is, but the null is that they're the same. But what about the sigmas? So you get a standard deviation. We call it sigma for the population. And we get a sigma here. And then these are assumed to be the same. That's why we're estimating them. We're estimating them from the sigmas we got here, but not these. We're estimating from these SDs here, but not these. What we're doing is we're pooling together all of them. We're doing a pooled estimate. So we're taking a weighted average of the variances of each sample. And that's exactly what this is. It's the weighted average. See, it's like the first step on the way to the variance. We're tweaking it slightly. If we divided by the whole sample size, then it would just be the variance. And then we would take the average. Instead of dividing by, that, we'd divide by n. And then we'd get the standard deviation within each one as a weighted average of their variances. Okay? That's what we're doing. So here, what we have here is we're going to estimate both of these to be the same. So this one and that one are both going to be estimate to be right there. That's our estimate to be 3.18. That's what we're doing here. Okay? So it makes our calculation easier. So this right here, I say, because the square root of the mean square within is what? Is a pooled estimate of sigma within each group. This is the sum of squares within each group. Then we divide, there's like the variance within each group, and there's the square root of the variance, which is the standard deviation. But it's tweaked with that because we're dividing by n minus the number of groups instead of n. Okay, so that is the deal. Now, how are we going to do this? When we have a pooled estimate, it makes our calculation so much easier. Because look, all right, so is the pooled estimate. So we can use that. So here's our formula. Now, what does pooled mean? It means that these two are the same. So we can factor it out. We can factor it out, right? And say, and then we get this, a simplified. Simplified. All right? So let's do that. We can see how it works. So we're going to say what? We're going to take our t, which is our observed difference minus our expected, but that's just 0, over our standard error plus for the difference. And so we get, we're just going to say the difference here. And it doesn't really matter which way you subtract because we're going to do a two-sided t. So that's our difference. And that is 1.795. So is that difference big or small? Well, we don't know until we find out what the standard error is. So now we do the standard error, so what are we going to do? Okay, so I'll do it before we simplify. So we do this, we're taking the square root of, and then it's going to be this 3.18 SD, that's SD plus, like over the square root of n, so over the square root of 84 squared, plus I'll do the same for the other group, 3.18 over the square root of 99 squared. Okay, so that's what it is. And then when I simplify this, do you see how you can just pull out that 3.18 and get, I have to move this over a little more. Let me move this over here, 1.795. And so this is going to be 3.18, factor that out, times the square root of 1 over 84 plus 1 over 99. See? So it's so much easier. You don't have to take the, look what we're doing here. We're taking the square root, then squaring them, and then taking the square root again. This is so much easier. All right? Does that make sense? So let's do that. I did this, and I got, what did I get? A t statistic of 3.804. This, by the way, I got something like 0.47, which again is bigger than either one of them, but smaller than the sum. All right. So now what are we going to do? So, oh, excuse me. Disregard what I just said. I'm glad I didn't write it down. I would have had to, what I said I got 0.47, but I would have had to compare that to 3.6 divided by the square root of that. So ignore what I just said. It's good I didn't write it down, right? Okay. So any questions so far? That's our t statistic. That's a lot of work to get it, but it was a lot of explaining. So now what can we do? Now, let's say we're not doing multiple comparisons. If we weren't doing multiple comparisons, what would we do? Well, first of all, we have to get the degrees of freedom. There's a whole bunch of, we're going to compare it to some t-curve, but we don't know how many degrees of freedom. So how do we get the degrees of freedom? Before we were saying the degrees of freedom minus 1 were the sample size minus 1 of the smaller one. So that would have been 83. But that's not what we're going to do here. No. We're not going to do that here because why? Well, the degrees of freedom for the t-test is going to be exactly the same as the f. It's going to rely on all n minus g points because that's what went into our calculation, right? This is, it's going to be the same as the degrees of freedom in the f-test because we're basing our estimate on data from all the groups, even though we're only comparing 2. We said they're all the same, and we're using all that information to get a much better estimate so we can have much more degrees of freedom, much more precision. More degrees of freedom means you get closer to, you have less error. Okay, so this is going to be the degrees of freedom will be what? So we have this, and the degrees of freedom are going to be equal to n minus g. Say 858 minus 5, which is 853. So let's just alert. So this is the same. These are the same. And what else are we getting? Where are we getting these numbers from? So there's this 84, the 99. What else do we have here? And this right here, you know where that comes from. And then this difference is this, the difference between those two. Okay, so that's what we've got here. And now we can draw that picture. And let's draw it. I had to look it up on the calculator, right? But I did, and I got, what are we doing here? Between, so this is 3.804, this is negative 3.804. As a z-score, as a difference, this is where that lined up, that, what was it? This, set 1.795. Oh, so sorry. That's where it lined up. So here's is our z, this is our z, but is our value You'd expect 0, but it lined up there, and it's very, very big. So our p-value is going to be both tails. And it turns out to be, this is a tiny, tiny, it's way out on the tails. And I got a p-value, so the p-value, the area of both tails, is equal to what? This is a tiny p-value, 0.0152%. Now, so far so good. So the only adjustment we made from our usual t-test was pulling the standard errors, the standard deviations into one estimate, okay? That's the only thing we did different. But now it says use the Bonferroni correction. So before we do anything, we have to make a we're going to have to understand how we have to, this is the p-value if we didn't cherry pick this result out. I already looked through all these comparisons, and I picked out what I thought, here's the biggest one, and here's the smallest one. So it's like running, I cherry picked that out. If I hadn't seen that, this would have been our p-value. But these are called post hoc tests, right? So how do we adjust? Where did I write that? I thought I wrote, yeah, right here. So t-test for post hoc, what does that mean? Post hoc test. That means, post hoc means that after is post. After this is what it means, but after looking at all the data, all the comparisons. We picked out the one that was biggest. So this means after looking at the data. Post this, after looking at data. Okay, so I looked here and saw and cherry picked this out. Now that's cheating. That's data snooping. Remember we talked about this. Why? Why is it data snooping? Because how many possible comparisons are there? Well, I could have compared whites to blacks, Hispanics, Asians, and Mexicans. Then I could have compared blacks to whites, Hispanics, Asians, and mixed others. So there's 5 for each of these 5 groups. I could have made 4 comparisons. So that's 20 comparisons if I cared about the order. So let's look at this. So we have to adjust our p-values for the number of comparisons we make. So we're basically performing multiple comparisons. So what do we have to do? We have to adjust for that. We're going to have to multiply our p-value for how many comparisons we made. So with 5 groups, how many pairwise comparisons are possible? With 5 groups, let's think. How many pairwise comparisons are possible? Well, why don't we think about it here? Let's just write it down here. I just started to do that. What did I say we could do? I know a lot of you know how to do this anyways, but just to make it really vivid, I could have done whites, 4 for whites. Whites minus blacks would be one comparison. Whites minus Hispanics, whites minus Asians, and whites minus other. And then I could have done that for each of the 4 groups, right? I could have said blacks minus whites, blacks minus Hispanics, blacks minus Asians, and blacks minus others. Do you want me to write them all out or not? Do you? Okay. So then I could do it. It won't take long. Hispanics minus whites. Who else is there? Hispanics minus blacks, Hispanics minus Asians, and Hispanics minus others. And then what other? So then who else do I have now? Now I have the Asians. So the Asians minus whites, Asians minus blacks, Asians minus Hispanics, and Asians minus others, and then finally the others. And then the others minus the whites, the others minus the blacks, the others minus the Hispanics, and the others minus the Asians. So that is 5 times 4 comparisons. So that's 5 groups times 4 comparisons for each of them. So that's 20. But now I said order didn't matter. So whites minus blacks is the same thing as blacks minus whites, right? I don't care which way they go. And blacks minus Asians is the same thing as Asians minus blacks. So I have to divide it by, so these are 20 ordered pairs, ordered comparisons. But we only care about unordered. But only 5 times 4 divided by 2, which is 20 divided by 2, which is 10 comparisons, if we don't care about ordered. Unordered comparisons. Okay, so that means that we're going to have to take this 10, I'm just going to jump ahead, this 10, because we made 10 comparisons, and how are we going to correct our Bonferroni? And I'll explain why, but first let's do it. So this is our p-value. If we didn't look at the data first, that's our p-value for one comparison. If we didn't, but now we have to use this. But we need to multiply p times the number of comparisons that we're really making, and we're picking out one. So we're going to take that, and the number of comparisons is what? We already said it was 10. We're going to say number of comparisons, and this is equal to what? And this is equal to 5 times 4 over 2, which is 10. So we're going to take that p-value of 0.0152, and we're going to multiply it by what? Times 10, and that's our p-value, 0.152%. It's still significant. That's our p-value. That's called the Bonferroni adjusted p-value. Any questions on that? All right. So let's just explain the reasoning for a few minutes, and then I want to get started on correlation. So what is the reasoning here? So, oh, is that good? Did everybody copy that down? Okay, so I said how many groups, okay, with 5 groups, with G groups, so we said with G groups, there's G minus 1 comparisons for each group. So the general formula is, so G times G minus 1, and then we have to divide by 2, and this is equal to how many unordered pairs? Because we're not specifying a direction. So with 5 groups, we'd have 5 times 4 divided by 2, which is equal to 10 comparisons. Okay, so now, all right, so here is what we're going to do, because we're making 10 comparisons at once, okay? I mean, if you want to, so we could set our significance level. If we set our significance level at 5%, then what's the probability of getting at least one significant difference just by chance? We want it to be 5%, but that's just for one comparison, right? If we have the probability of at least one is 1 minus the probability of none. So 1 minus the probability of none, that's 0.95. For one comparison, 1 would get 0.05. That's our 5%. But if we do it 10 times, we have to multiply that each time we want a non-significant result. So that's 0.95 times 0.95 times 0.95, and that's getting smaller and smaller and smaller. So we end up with 40%, not 5%. So that's why we have to make these adjustments. Okay? So, so now, let's say, so what do we do to make the adjustment? So we have 10 pairwise comparisons. So our adjusted Bonferroni to reject the null is going to be that. We're going to use that to reject the null. All right? And this, all right. So we're going to use that. We're going to divide it by 10. That's the same. Alpha divided by 10 is the same as multiplying our p-value by 10. Okay, that's the same. All right, so if you do the calculation then, we get, okay, so now we do it with the alpha equals not 5%, but 0.5%. See? And now we get what we wanted, very close to what we wanted. Why is this the same? If you don't know, it's just, okay, so instead of 5%, instead of p less than 5% to reject null, we need p less than 5% over 10 to reject the null, right? Which is the same thing as what? P times 10 has to be less than 5%. It's the same thing. Okay. That's just a page number. All right, so that's the idea. And now let's turn the page and see if there's anything else we need to talk about. Here's the summary, so that's good. And there's just basically two situations that are really important. If we single out before, then no adjustment has to be needed, none. But if we single out after, post hoc, then we have to do this. Then we have to multiply p by this. Okay? Before we do nothing. And what it is, it reduces the probability of a false positive. So any questions so far? That's ANOVA. And we're going to revisit ANOVA again after we finish regression because it's going to be a special case of regression. So we're going to go back and revisit it, and that's where it will make more sense why it's called the between groups are called the model. Okay, so now let's see what we're going to do now. So we do this, and now we're on to correlation. So I just want to do, this will be very fast. And I know it's kind of tedious, but otherwise we won't get through. And this is so simple. If you're in Stat 100, you will love it. It's just so easy. It's just like what we did in Stat 100. And it's very simple. So now what are we doing? Simple regression. What is regression? So we use this graph when we have the relationship between two quantitative variables. We're going to make a scatter plot. We haven't had two quantitative variables yet, two numerical variables. We're just comparing groups to a numerical. Okay, so one variable is assigned to the x-axis. That's like the predictor variable or the independent variable. You think it's predicting the y variable, which is dependent on it. Okay? You think the independent variable, like this is the independent, is like a predictor variable. It's thought to influence. This one's dependent. It's getting predicted. The y is getting predicted by the x. So this is usually x, and then the dependent is y. It's what you're predicting. You're trying to see if x is a good predictor of y. So you set up these, and then you have something called the correlation coefficient R, which measures the strength of a linear association between x and y. It measures how tightly the points cluster around a line, not a curve. Okay, so R, this is, you're not going to use linear regression and measure, is R appropriate for the plots below? No. I mean, here we have a quadratic. We could make a great prediction of y from x, but you know what R would do? It would try to fit a line through here. It would look at, and it would say there's no correlation. So it's completely inappropriate. No, because we have a curve. This is what regression would do. R would say there's nothing here. You can't predict So it would be a terrible thing to do. Here it's great. Yes, we can use R, and R would measure clustering. This looks like R is 1. There's almost looks like a perfect linear relation. Here's a problematic because we really have two graphs, both with negative correlations. But if we actually used R on the overall, it would fit this, and it would do this. So it would say it's positive. This would be an example of confounding. This would be like a confounding. We'd have to split it into two groups. Because both groups have negative correlations overall, this would be an example. So here, no, we can't use the overall. So no split graph if there are two prior groups here. There's two groups, two distinct groups. Okay, what about this one? You might think no, but you know what R would do? It would say, it would fit, okay, it would be almost no correlation, because what does it mean? No matter what you have on X, you can't predict Y. And the best fit would just be a line, a horizontal line. There'd be 0, so this would be, yes, this is good to use it, because it accurately says that as X gets larger, we can't tell anything about Y, right? As X gets bigger, Y doesn't change. You can't tell anything, and that's true. So that would be a good use of it. And of course, this one's good too. So yes. All right? So this is not as strong a correlation as that, but it's positive. Okay, so R is between 0 and 1. It's not negative. So this is correlations go between -1 and 1, and the closer the points hug a line, the closer with a positive slope. So what is this? So if it's a so this is, I'm just looking at the positives here. So this is R equals 1. Perfect correlation down here is R equals -1. And this is like R equals 0. So that's how you should, these are points here. They're supposed to follow a line. R equals 1, R equals 1, -1, 0. Okay. Means you can perfectly predict one variable knowing the other. That's true. If you have this, you can perfectly predict it, but the opposite isn't true. I mean, the converse. You can perfectly predict maybe, but that doesn't mean R is equal to 1, because you could have a curve. Okay, so now these plots, this is in our data program, all have the same averages. They're all within the same standard deviations for X and Y, so it's very easy to compare them. And so now you might want to match the correlations with their scatter plots. And they're all scaled to the same, basically, there's 5 statistics that describe a scatter plot. There's like the point of averages, which is right in the middle, right? The average of X and there's the average of X, the average of Y. There's the standard deviation of X and the standard deviation of Y. And then there's the correlation coefficient. These have all the same, these have all X averages, Y averages, X standard deviations and Y standard deviations are all the same. They're all this, oh, you can't even see that. X average, Y average, XSD, YSD are all the same in the 4 plots. So basically this box is the same. So what's different? It's R is different. R is what's making it look so different. And I just ran out of this, so I can't do this anymore. Okay, so that's what's, boy, does that look bad? But you get the picture. Okay, so now let's just, so we got these, so that's what makes them look so different, is just the relation between our X and Y. So this one looks like there's no relation. Which ones are wait a minute, we have to look at what we have here. We have a two negatives and two positives. This one's a strong positive, so which one's the strongest positive is going to be which one? 0.88. So that has to be B, right? Is that correct? And then, what's the strongest negative? This one's the strongest negative. It's going down. So that has to be, that's negative 0.68, so that has to be C. Then one of these is slightly positive and one slightly negative. Gosh, this looks slightly positive, doesn't it? Or does this one? This one looks slightly positive, so it's got to be this one, D. And this is a negative one, so that's apparently slightly negative. So that's A. Okay? Does that make sense? Okay. And now what are we going to do? So it measures, so we said it measures how closely, R measures how closely the points hug a line. Well, what line? It's the line of equal standard deviations. So it's the line, it's called the SD line, and it goes through the point of averages, and the slope of the SD line is equal to rise over run, so you go over one standard deviation in the x direction, you go up one in the y direction. And that's the line as opposed to the correlation line. This is the line the points are hugging. In other words, every point on the line has the same z-score. Once you change to z-scores, the SD line has r equal to 1. And that's the same as r equal to negative 1. And that's the same as the line of zx equals zy, or zx equals negative zy. That's all the same. Let's see how it works. So they all have the point of averages. So for this data, where's the average? So we have an 83 on the midterm and a 74 on the final. So let's find that point on here. So here's about 83. We go up here. And 70 here, 74 I'll put right there. And this is 83. So it's where those two intersect. That's the point of averages. That's the point 83, 74. That's always on the standard deviation line. It's also always on the regression line, which is a different line. All right, now what do you do to get the next point on the line? 2 points determine a line. We're going to go over one standard deviation in the x direction, so we'll go from 83 to 92. This is one standard deviation in the x direction. And then we're going to go up one standard deviation in the y direction, that 10, from 74 to 84. So we're going to go up here. And that's one standard deviation in the y direction. And so now we get the point 92, 84. And it's like this. And this is our SD line. And if you go over one standard deviation above average, this is our average, this is the point of averages. One standard deviation above average in both directions. Another word in z-scores, this is 1, 1 in z-scores. And this right here in z-scores is, what's that in z-scores? That's the point 0, 0 in z-scores. Okay, so that's the idea. This is the SD line. Later we're going to look at something called the regression line, which is different than this. It's our best estimate of y given x. But this right now is this, and so we got all that. And now, how do we get the correlation coefficient? Well, the correlation coefficient, you know, we use these z-scores because why? We're comparing how close the lines are to this perfect correlation. If there's a perfect correlation, the z-scores all match up. It's like a standard measuring stick These are in different units. They have different standard deviations. One could be inches, the other could be pounds. We have to change them to z-scores to assess the correlation coefficient. That's in pure units. So that's why I'm alerting you to this. This is in pure, once you get the SD line, that's in pure units. I'm showing you basically what the correlation coefficient is. All right, so the correlation coefficient is once you convert to z-scores, it's the average of their products. So let's convert, let's do this example here. Here's x's, right? So this is zx and this is zy. And what we're going to do is we're going to multiply them together and take their average. All right, so let's say I told you, so we have 4 x's here. And let's say I said their average of these 4 x's is 7. And the average of these 4 y's is 8. And the standard deviation of these 4 x's is 2.5. And the standard deviation here is 1.6. So now we just convert these to z-scores by doing what? Well, value minus the average over the standard deviation. And we get 1.2. And we'll do the same for the y here. 10 minus its average over its standard deviation. And I got 1.25. And by the way, this point I should have graphed it, but then I multiply these two together. 1.2 times 1.25, and I get 1.5. Then I do it with all of them. So I'll just tell you what I got, and you can check it. I got 0.8, negative 0.625, because this is below average. So above average, below average, when you multiply them together, you get a negative here. That's like a negative correlation when above average and below average. Above average in one and below average in the other. Same here. This is negative 0.8. This is below average, but this one's above average. So this is positive 0.625. And when I multiply these two together, this is what I'm doing, I get a negative, because they're opposite. One's above and one's below. Once you change it to a z-score, and now you get a negative. Now we'll do these. These are both negative, times another negative, and we're going to get a positive. All right, so the idea is, if I graph them all, the point of averages, just quickly, is 7, this is the average, and 8, this is the average. So right here, let's just divide into 4 quadrants. Okay? I did that wrong. I should have done it 7. Oh, look at this, an erasable pen. Cool. Okay, so now we did this 7. And now it's good. Okay, so that's the average, and that's the average. Okay, so the positive times the positive is going to fall right here. This is 10, 10. And that's why we get that positive right there, right? Product. The negative times the negative, that's 4, 6. It's going to fall right there, and that. But you see, right here, if you have if it looks like this, you have a positive correlation. Negatives associated with negatives, positives associated with positives. Now the other two fall along in these quadrants, where you're going to get negatives when you multiply them. So this, we have 9, 7. Excuse me. We have 5, 9. And 9, 7. Right here. And these two give you the negative, these two. But you see how this, we're going to get an overall positive correlation because these two outweigh those two. So when you add these together, the positives, if you sum those up, we have 1.5 plus negative 0.5. These two are negative. But they're not as large in absolute value as the positives. So we get a positive 2 over 4. So it's 0.4. That's what R is. You see, if these two were out this way more, then we'd have a negative correlation. So basically, it's the strength of, because what is a positive correlation? Below average values of one variable are associated with below average of the other, and same and above average with above average. And so then that's the idea. So that's the idea of the correlation coefficient, and it measures things in terms of standardized scores. So I think that's pretty much it, and I can post, you'll be able to do a lot of some of Monday's homework, not all of it. So we'll finish up, we're going to try to finish up this simple regression on Thursday. That's it.